Good day, grade 12 learners and teachers. Welcome to today's mathematics lesson. My name is Mr. Shongwe, and this lesson is brought to you by the Gauteng Department of Education in collaboration with the Saibono Discovery Center. Right, good people, today we are looking at probability, but the subtopic would be the counting principles. We are going to look at the fundamental principle of counting. Okay, let's begin. Now let's first look at our lesson objectives. Remember, this lesson is a continuation from the lesson you had last week on just probability, which we looked at the revision of grade 10 and 11 concepts that are examinable in grade 12. So it's part and parcel of what you'll be writing on when you write your paper one, all right? Now, by the end of the lesson, you should be able to understand the origin of the fundamental counting principle, where did this principle start, all right? And then understand the factorial notation as a way to congest the big products that we work with in the fundamental counting principle. We should be able to use the fundamental counting principle to arrange objects without repetition. Those simple objects where you just play around with them and arrange, please think of this as a practical thing, all right? It's a practical thing. It's just that at times you then work with big numbers. That's where now we need to bring in those permutations, those factorials and so on. But please think of this as something that can be done practically. You can actually have flashcards that you can rearrange and see how many arrangements are possible. All right, it's a very practical section of work. Okay, so you need to be open-minded as we play with these arrangements. You should also be able to use the counting principle to work with seating arrangements, book arrangements, and weight arrangements, all right? Where restrictions are now permissible. And then you need to also be able to work with the fundamental counting principle to sort out problems involving digit numbers and codes. Remember, at times you will have a combination of numbers, codes and letters, all right? Especially if you are talking of passwords, to say the password must contain 2 letters, must contain 2 numbers, all right? So you can have a combination of those, all right? And then also use the counting principle to arrange identical objects, all right? So that's part and parcel of what we need to know. If we are dealing with objects that are identical, the counting procedure there needs to be altered just a bit to make sure that we take into account those repeated objects there, all right? If you are dealing with identical objects, should also be able to use the counting principle to count the rest of the items in situations where it is not practical to physically count the assortment. So we are going to be using the not rule, all right? The not rule. So this speaks to the not rule, all right? The not rule. So we'll be using the not rule here to try and count those possibilities by counting by difference, all right? We'll be exposing you to that. We should also be able to use the fundamental counting principle to solve probability related problems. Remember, we are in probability, all right? So we should also take to cognizance that probability being number of elements in the expected set divided by the number of elements in the universal set, that is the sample space, all right? So we also need to know that the counting principle can also be applied to probability related problems, all right? Remember, the section of work is probability, all right? We can actually refer to the policy document here, which is CAPS. You'll find that on page 49, which speaks to the depth or the scope within which we operate when we do our fundamental counting principle. You will see that it is prescriptive to say that the use of combinations is not examinable, right? So we do not use any combinations at this particular level. We just arrange in a straight line, okay? So also the exam guideline will also talk to the the fact that we do not use the combinations and we do not also use the conditional probability. Okay, so it tells us about the scope within which we operate when we teach the counting principle and also when exams are set on the counting principle. All right. The knowledge that you should be bringing in, it's the knowledge that we worked on last week. You should be knowing the terminology. You should be able to work with compound events. Remember, these compound events will bring rise to the use of the probability tools like your Venn diagram, your tree diagrams, and your contingency tables. That's how we deal with the compound events, right? Complementary events as well. This will assist us a lot when we work with the NOT rule, all right? Mutually exclusive and inclusive events, all right? Independent and dependent events, exhaustive events, and so on. Probability equation and probability identities. That's the prior knowledge that one should be bringing into this particular lesson. All right, moving on, let's look at now the baseline assessment. All right, I've set this up. In our baseline assessment, you are required to go back to the knowledge of your grade 11, all right, and try to solve this for me. Okay, I'll go and read it out for you. Use a tree diagram. You see, this is prescriptive. Use a tree diagram to determine the total number of outfits possible when you are given 3 t-shirts and 2 trousers, all right? And then you answer the second one as well. Is it practical to use the tree diagram if you are to be given 120 t-shirts and 350 trousers? Okay, here you can see it's just 3 t-shirts and 2 trousers, and then they are asking whether it will be practical to use a tree diagram if you are presented with 120 t-shirts and 350 trousers. All right, so I am just going to give you 5 minutes. Okay, 5 minutes to work with this baseline assessment. All right, your 5 minutes time starts now. Right, hello and welcome back. I hope you were able to work around this problem. It just unlocks our thinking and allows us to transition nicely to what is expected of us in the counting principle. Right, good people, please make sure that you also check us on our WhatsApp interactive number 079-578-2908. We are there to assist you if you have any questions based on the current lesson on the counting principle. Please make sure that you ask those questions so that you are assisted, so that by the end of the lesson you are moving together with us. All right, I think the number is popping down now at the bottom of your screen. All right, let's look at the problem. Use a tree diagram to determine the number of outfits possible when you are given 3 t-shirts and 2 trousers. All right, we just want to know and visualize. Remember, a tree diagram is a visual tool that allows us to visualize those outcomes and allows us to work with the probabilities of those outcomes in an organized manner. All right, that's what the tree diagram does. All right, look at this now. Obviously you can see we have two or a total of outfits when you are given 3 t-shirts and 2 trousers. So when we have our tree diagram here, you can see we have 2 trousers. So we have trouser 1. We are going to let trouser 1 be given by what? T1, and trouser 2 be given by what? T2. And then we let t-shirt 1 be given by S1, t-shirt 2 S2, t-shirt 3 S3. All right. Now, if you check here, we have trouser 1 and trouser 2. We are not interested in the probabilities for now. We just want to visualize those outcomes. Trouser 1 can be worn with t-shirt 1, t-shirt 2, or t-shirt 3. So this gives us the first outfit, which is trouser 1 and shirt 1. This is the second outfit, which is trouser 1 and shirt 2. This is the third outfit, which is trouser 1 and shirt 3. Trouser 2 as well can be worn. Trouser 2 can be worn with shirt 1, shirt 2, and shirt 3. So the outfit would be trouser 2, this should be T2, trouser 2 with shirt 1. Allow me to just write down the correct one here. Trouser 2 with shirt 1, trouser 2 with shirt 2, and then trouser 2 with shirt 3. All right, let's discard this one. All right, so that's what we should be having. So this would give us the third outfit, the fourth outfit, the third or the fourth outfit, the fifth outfit, and the sixth outfit. So you can see the total number of outfits here would be equals to 6 possible outfits there. All right, it's 6 possible outfits there because it's 1, 2, 3, 4, 5, and 6. All right, using the tree diagram, so we can be able to visualize these outcomes and arrange them in a very organized way. T-shirt 1, trouser 1, shirt 1, trouser 1, shirt 2, trouser 1, shirt 3, trouser 2, shirt 1, trouser 2, shirt 2, trouser 2, shirt 3. All right, so that is the organization there. Now, let's look at the second question. The second question says, is it practical to draw a tree diagram if we are given 120 t-shirts and 350 trousers? Imagine now we have trouser 1 and trouser 2. Imagine if we had 350 trousers. It means that we were supposed to have 350 of those sub branches, with each branch associated with 120 different possibilities. So to draw a tree diagram for this one is possible, but it is not practical. You cannot be able to do it, otherwise you will take more than 3 hours, and you are only having 3 hours to write the whole paper. you'll be taking more than 3 hours just to draw this tree diagram. It is possible to draw it, but it is not practical and it is very tedious. And as mathematicians, we need to revert to much easier ways of being able to count when we have such possibilities. All right, so we define different rules that would allow us to simplify something that was going to be tedious and make it easily accessible. All right, so we are going to say, yeah, it is not practical. It is possible, but it is not practical drawing 120 branches and 350 sub-branches per branch. It is time-consuming and very tedious, and it is not going to make you a better mathematician to be able to do that. So a better mathematician finds simpler ways to be able to do this thing. So the way that we are going to use here to be able to simplify this would be our counting principles. All right, so let us look at the background. All right, when mathematics began, we began by counting, all right, using fingers 1, 2, 3, 4, 5, 6, and so on. So when you add, you will say 1 plus another 1. If I count, it's 2. All right, so that's how our mathematics started. And then we moved on to cold drink lids. You'll remember at elementary school, primary school, we used to collect a lot of those cold drink lids. We count them. We use them as our elementary mathematics to count, to say if someone says you take 5 and you subtract 2, you are going to take 5 cold drink lids, and then from there you take away 2, you check how many remain. So that is what we used in our elementary schooling. That's how mathematics began. All right, but now this is only practical for small numbers. If someone would say 100 minus 50, taking cold drink lids for that would not be practical. So what happens when we have large number of items that need to be counted? Then we need to develop a principle that would allow us to do that. In this case, we are going to be using the fundamental counting principle, or we can use any other mathematical techniques to be able to work with different assortments. All right, so that is where the fundamental counting principle finds its space. All right, now let's look at the introductory example. All right, we are going to continue with our tree diagrams, but we are introducing the principle. Look at this now. A coin is tossed once. How many times? How many outcomes are there? So that's where you need to find your head on your tail, and you say, oh, I have 2 outcomes. All right, and then you count 1, 2. If it's tossed twice, how many outcomes? It's tossed 3 times, 4 times, and then we go straight to 20 times. So we have 1, twice, 3 times, 4 times, and then we shoot straight to 20 times. All right, let's check here how we can be able to work with that. Check if it's tossed once, that is the only draw. So how many outcomes? It's 1, 2 possible outcomes there. All right, so we indicate there are a total of 2 possible outcomes when a coin is tossed once. Let's check when it's tossed twice. All right, head and tail. All right, for the first toss, and then for the second toss, if the first toss gave us a head, there's a possibility that the second toss might be a head or a tail. If the first toss gave us a tail, there's a possibility that the second toss might be a head or a tail. So the outcomes, you see 1, 2, 3, 4. You have 4 different outcomes. All right, so we can check here the explanation. There are 2 possible outcomes for the first toss, that is the head and the tail, and there are also 2 possible outcomes for the second toss, that is also a head and a tail. So there's a total of 2 times 2, which is 4. All right, so you can see now we are developing something here. We are multiplying the 2 for the first outcomes and the 2 for the second outcomes. We get 4, which is the same as what we see here, what we can visualize using a tree diagram. All right, let's continue and see what happens as we go on. Let's assume that it is now tossed 3 times, the same coin. You toss it for the first time, you get down the outcomes, head and tail. You toss it for the second time, you get the outcomes. You toss it for the third time. So first toss, it's a head and a tail. Second toss, you could draw those 3 diagrams. If the first one was head, then we have possibility of head or tail. Third toss, same thing. If the first one was head, you have possibility of head or tail. So you can see the outcomes there. They are represented in a way that we can visualize them and we can count. So you can see we have 1, 2, 3, 4, 5, 6, 7, and 8 outcomes. All right, we have 8 outcomes. Let us summarize our findings here. All right, let us summarize our findings. There are 2 possibilities for the first toss. All right, there are 2 possibilities, which is head and tail. There are also 2 possibilities for the second toss, which is head and tail. There are also 2 possibilities for the third toss, which is head and tail. All right. So if we multiply the individual possibilities, you can see it's 2 times 2 times 2, which gives us 8, and which is the same as the 8 that we physically counted there. All right. So we are developing something here. You can see we are trying to develop something here. All right. So let's move on and see. Tossing 4 times, all right. You can see now it's now getting a bit difficult to even put head or tail, head or tail, head or tail there. It's becoming increasingly difficult because the number of branches there are increasing. So you can see the first outcome will come out of here, the second outcome will come out of here, the third outcome will come out of here, the fourth outcome will come out of there, the fifth one will come out of there, and so on and so forth. So, but you can see that now it's becoming a bit difficult to do it, all right, using a visual tool, which is a tree diagram. So it's becoming a bit more difficult to actually align those individual branches there, all right. So let's check here. All right, using our method there that we were trying to actually build up when we started. There are 2 possible outcomes for the first toss, that is head or tail. There are 2 possible outcomes for the second toss, that is head and tail. There are 2 for the third, 2 for the fourth. If we multiply all of them, we get that it's 16 possible outcomes. All right, so this is assisting us. This is assisting us in terms of getting the outcomes. We are multiplying those individually. All right, the number of possible outcomes per toss. All right, now let's now look at 20 times. All right, is it now practical to draw a tree diagram for 20 tosses? It is possible, but it is not practical, and it is very tedious and time consuming. All right, so let us check now what we have there. It is increasingly becoming difficult to use a tree diagram to determine the total number of outcomes for more than 3 tosses. You saw with 4 we struggled. Hence, we shall try to generate a pattern to determine the total number of outcomes. Consider a table below. If the number of tosses is 1, we have 2 possible outcomes. If it's 2, we have 2 times 2, which is 4. It's this 2, all right, times the 2 for the second toss, which gives us 4, and then we have the 2 and the 2 again for the first and second, times the 2 for the third, which gives us 8, 2 times 2 times 2 times 2, which gives us 16 for the, if we have 4 coin tosses. From the above, we notice that when we multiply the number of options available in each of the coin tosses, all right, we multiply the number of options available per toss of a coin, we can now be able to generate and see that if we are doing it for 20 times, we would have that this is 2 times 2 times 2 up till 20. So this takes you back to what? To number patterns, all right? This is a perfect example of an exponential or a geometric pattern, all right? So now you can see that it's then 2 to the exponent of 20, which gives us here a number that is greater than 1,000,000 there, all right? A number that is greater than 1,000,000 there. So we can use that particular number there, which is 1,485,000 and then 76 there. So we can then use that number to actually say if we've done it for 20 or we've tossed it 20 times, all right? Now, let us look at now the basic application of the counting principle. Now, this counting principle that we've generated from the previous slides, it allows us to count the total number of outcomes in a situation. Now, how do we use it? Let's look at the rule of product. It says, the counting principle states that if there are m ways of doing task 1, n ways of doing task 2, r ways of doing task 3, and so forth and so on, if you have many different tasks, then to do all the tasks combined, the total would be m times n times r times, as you continue with those ways, all right? So if you have 3 tasks, you would have m ways of doing task 1, n ways of doing task 2, are ways of doing task 3. If you want to do all of them combined, you will multiply the number of ways that are taken in each task. All right. So we are concerned here with the number of options available of executing a task. We are not concerned with actually how the task is executed, but the number of ways in which we can do it. All right. So you are not going to choose. If you are saying you have 3 t-shirts, it's 3 options. Although you are going to wear 1 t-shirt, but the counting principle is not concerned with the number of t-shirts that you are going to wear, but it is concerned with the number of options that you have of wearing those t-shirts. All right, so that's very, very important. All right, that is the fundamental counting principle. All right, now let's build up to this by looking at an example. All right, this is a basic application example. At a school's fundraising event, each person who wishes to buy a meal may choose only one food item. All right, only one food item from each of the following 3 tables. So at the end of the day, if you have Mr. Shongwe to choose here, he must choose 1 in table 1, 1 in table 2, and 1 in table 3 at the end of the day. But that's not what the counting principle is concerned with. The counting principle is concerned with the options that he has of choosing a specific food item. So that is very, very important and key as far as the counting principle is concerned. All right. So now let's check the options that he has for table 1. He has 1, 2, 3, 4 different options. All right. You can choose a hamburger, vegetable burger, or steak roll, or it's only 3. All right. It's only 3. My bad here. It's only 3. It's the hamburger, the vegetable burger, or steak roll. So it's only 3 food items that he must choose from. He can only select 1, but the options are 3. All right. And the counting principle is concerned with what? The options. All right. Table 2, 1, 2, 3, 4. He has 4 different options there. All right. Table 3, he has for dessert 1, 2. It's ice cream or it's fruit salad. So he has 2 options. So how many different meal combinations are possible? All right. So let's look at how we should be working that out. We look at table 1, the number of options in table 1, table 2, the number of options in table 2, table 3, the number of options in table 3. So he is executing 3 tasks, right? Those tasks involve selecting a food item from each table. So for him to execute that task, then we need 3 options here, 4 options there, and 2 options there. And according to the rule of product, that is the fundamental accounting principle, we should multiply the number of options that we have in each task. All right. So to get the total meal combination, we are multiplying the options for table 1, 2 options for table 2, 2 options for table 3, and then we get 24 different meal options. All right. So that is how we use the counting principle. Let's go on. There's an activity here. All right. There's an activity. I'm just going to give you again here 5 minutes. All right. Let's make it 4. All right. 5 minutes would be a lot for this simple activity. Just 4 minutes. I want you to work on that quickly. All right. Just work on that quickly for 4 minutes, and your time starts now. Right, hello and welcome back. Remember, we are available on our WhatsApp interactive number on 079-578-2908. You can ask any questions based on the lesson that is ongoing now on the counting principles. Right, let's check the activity that I gave you. A car dealership offers the following car types. Body styles, that is sedan or hatchback. So we have two body styles options, all right? And then the color, which can be red, black, white, gray, or blue. All right, so we have 1, 2, 3, 4, 5 different options. And then the model can be a standard model, can be a sports model, or a luxury model. So we have 3 options. How many car options are possible? All right, so we are going to look at the, all right, we are going to look at the total options, all right, total car options. You can see with the first one, we have 2 options for the body style, all right, multiply by, we have 5 options for the color, all right, multiply by, we have 3 options for the model. All right, the model is 3 options. So we would have that the total number of options would be 2 times 5 times 3, which gives us a total of 30 car options. 30 car options are possible there. All right, let's look at the second one. Suppose that you decide to buy a hatchback, all right? So what are you doing here? You are saying, I am taking away the sedan. So you have 1 option remaining, all right? Because you are going for the hatchback. However, the hatchback can come in all these colors. So you still have 5 options for colors, and you still have 3 options for what? For the model. All right, so how many options are available to you? So still here, total car options. All right, this would be equals to, for the body style, you only have, this is 1, 2, 3, this is the body style, and then the color and the model. For the body style, you can only have a hatchback because you decide to buy a hatchback, which means you now have just the 1 option for the body style. All right, and then from there, for the color, you still have 5. All right, for the model, you still have 3. So this gives you 15 car options, different car options. All right, different car options, 15 different car options. So those are the car options that you have. Remember, if they like, they can ask you to calculate the probability of buying a hatchback. So if they were to ask, suppose that they asked you to calculate the probability of buying a hatchback, you'll say probability of buying a hatchback, which is event E, would be number of elements in the expected set divided by number of elements in the universal set. All right, so now how many options do we have of buying a hatchback? It's 15. How many do we have in our universal set? That is 30 different cars. So it's half the chances of buying a hatchback. Remember, they can bring in probability as well here. All right, so please do not forget the concepts of probability. There is nothing new that I did here. I took whatever that we had worked with, and the first part was the sample space, the second part was our expected outcome or the event. All right, now I want to now introduce a very nice notation which we are going to be using here. How many ways can 2 learners sit in 2 chairs? If you have 2 chairs and you have 2 learners, how many ways can they sit? Total number of ways, 2 chairs. The first chair is 2 options because any of the 2 learners can sit there. And then the second chair, 1 learner has already sat in the first chair, so the second one would be 2 times 1. All right, now if there were 3 learners, all right, how many ways can 3 learners sit in 3 chairs? 1, 2, 3 chairs. So first option, it will be 3 for the first chair because each learner has equal chances of sitting in that chair. Second chair, 1 learner has occupied the first chair. Now for the second chair, you have 2 options. For the third chair, you have 1 option because already 2 learners have occupied those seats. Now let's look at the third one. 4 learners in 4 chairs, 2, 3, 4. So this would be 4 times 3 times 2 times 1, using the same explanation that we've been using. All right. The last one, total ways. If we have 8 chairs, 1, 2, let me do it here. Okay, total ways. If we have 8 chairs, 1, 2, 3, 4, 5, 6, 7, 8. Using the same idea, we start with 8 learners, 8 options in the first chair. And then in the second chair, it would be 7 options because 1 learner is already occupying the first. And so on, here 6, here 5, here 4, here 3, here 2, here 1. All right. So now you can see that as the number of learners and the number of chairs increase, then the product that we are having now becomes bigger and bigger. So if I were to say 100 learners, all right, 100 learners in 100 chairs, all right, 100 learners in 100 chairs, it will mean you will have to now draw 100 dashes and assign those options to all those branches. So you see now it's becoming more and more difficult to write down these products, all right? These are products that decrease until they get to the number 1, but the more options are presented, the more difficult it is to count, all right? So we need to have a tool, all right? A tool that will allow us to simplify these big products, all right? That tool is called what? The factorial, all right? It is called the factorial. Let's see more about the factorial now. From the above examples, we notice that the number of options decrease successively by 1 until we reach the number 1. You can see when you have 2 learners and 2 chairs, it's 2 times 1. 3 learners and 3 chairs, 3 times 2 times 1. 4 learners and 4 chairs, 4 times 3 times 2 times 1, and so on. So we can see that these numbers decrease as you move, and then the lowest number is 1. They decrease from the highest, and the lowest number is 1. The highest and the lowest is 1. The highest and the lowest is 1. The highest and the lowest is 1. So we are going to then congest these big products by taking the highest number, the highest here is 2, and assigning the notation factorial, all right? By assigning this notation here, this is called what? The factorial, all right? In ordinary language, English, it is called the exclamation mark. In maths, it means a different thing. It is a factorial. It is trying to tell you, this sign here is trying to tell you that you have other products that are coming that are less than the number that you put before, but they go on to reduce to the number 1. All right. So now, if it's 3, the highest number is 3, and it decreases to 1. So we take the highest number and then we assign a factorial. The highest is 4. We take the highest number and we assign a factorial. The highest is 8. We take the highest number and we assign a factorial. So that is how the factorials are developed. And why are they developed? They are developed to simplify those 100 learners, all right, 100 chairs, where using the basic counting principle will become tedious because you would have to open 100 spaces. However, if you know it's 100 learners and 100 chairs, we can say it's 100 factorial, all right? So that is why we introduced the factorial. So what are they? They are a shorthand notation of writing down huge products that decrease successively by 1 until they reach the lowest number, which is 1. So when we have n, we are going to say n factorial is n minus 1, all right? We subtract 1 as we move n minus 2, n minus 3, and so on until we get to 3, 2, and 1. All right, and by definition, 0 factorial is equals to 1. This is a discussion for another day, not for today because of the time constraints. All right, factorials play a huge role when we arrange objects. All right, okay. Now, let's go on. From the introduction of factorials, we can develop another rule, all right? We've developed rule 1, which was the counting principle. Now we can develop another rule, which would be for the use of factorials. If you are arranging n objects, all right? N objects, and you have n spaces to arrange those objects in, then you can arrange them in n factorial. If you have 5 objects, 5 spaces to put them, it's 5 factorial. 4 objects, 4 spaces. So the number of objects available should be the same as the number of spaces afforded to put those objects, all right? So we can use the rule 2, which is a factorial. Now, look at what we have here. How many ways can we arrange 4 books in a shelf, all right? So we have a shelf. We want to arrange 4 books. All right, let's check now. In the first space, the second space, the third space, and the fourth space. In the first space, we have 4 books. So we have 4 options. Now 1 book is placed. Remember, you place 1, place 1. So what happens now? You have 1 less book. So how many options do you have? You have 3 for the second space. All right, you're going to place 1. So now that you've put in that 1, you'll have 2. Now that you've put in that 1, you'll have 1. And according to the fundamental counting principle, we can multiply those options, which is 4 times 3 times 2 times 1. But because it decreases to the number 1, we'll take 4, which is the highest, goes down to 1, so we'll say 4 factorial, all right, which gives us 24 ways, right? Right, let's move on. Arrangement of objects without repetition. Now, suppose that now you are presented with a different scenario. You have 4 books, but you have 2 spaces to put them. 4 books, 2 spaces. So 1, 2 spaces, 4 books. So this would be 4 for the first option times what? 3 for the second option. You can only place 2 books, all right? There are books that remain unplaced, all right? There are books that would remain unplaced. So the number of objects that you have is more than the space available to accommodate them, all right? So if we have that possibility, we can use now the permutation rule, another rule there, all right, which is rule number 3. If we have n objects and you want to arrange r at a time where n is greater than r, all right? The number of total number of objects are greater than the number of times you want to arrange them, all right? So now we are going to be using a different rule, which would be the permutation rule, all right? But we can always do away with it. We can always use our fundamental counting principle. So I will leave this permutation rule. I will not use it. It's part of the rules that may be used to solve if you can see the possibilities there are more than the spaces available to place those different options there. So now let's look at this. You have 10 different books. How many ways can you arrange 4? So it's 10 arrange 4. If we're working with permutation, we're going to say 10 permute 4. All right, and then we have the permutation button in the calculator, which would allow us to get the answer. Or you can use the formula there, which is 10 factorial divided by 10 minus 4 factorial. All right, but we are not interested more in those permutations there. We can also do this practically like that. All right, we want to arrange 4 books. So we have space 1, space 2, space 3, and space 4. All right. For the first space, there are 10 books, so you have 10 different options. All right. For the second space, there are 9 books, so you have 9 different options because you've already placed 1 book. For the third space, there are 8 options, all right, available. And for the fourth space, there are 7 options available. So if you multiply 10 times 9 times 8 times 7, 10 times 9 times 8 times 7 there, we get 50, 40. All right. This can allow us, you see, we had 10 factorial divided by what? 10 minus 4 factorial, which is 10 factorial divided by what? 6 factorial. If you go on to simplify that, you can see this would be 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, which is divided by 6 times 5 times 4 times 3 times 2 times 1. So this part here would divide that one. You are still left with 10 times 9 times 8 times 7, which is the same as what we have there. All right. So I will always encourage you to use the dashes and put in those options there as opposed to using the permutation rule. All right. Now let's move on. Obviously, there's the solution there for the spaces. All right. It's fine, we've already dealt with that. Remember, the counting principle can also be applied to solve probability problems. I'm just bringing this up so that when we get problems on probability, we can be able to solve them, all right? When we are given with such conditions, we are then going to use number of elements in the event or expected set divided by number of elements in the sample space or the universal set. So here we will need to clearly identify the sample space and the event as guided by what the question wants. All right, we'll see that when we apply counting principles to probability. All right, now let's go on into the business end now. All right. We want to arrange objects, but they are conditions, they are constraints. We want to know how to be able to deal with those conditions, all right? So please make sure that you follow us and you are with us as we work around this. It is a manageable set of work, but you need to make sure you listen and you listen to understand, all right? Now, in counting problems, we often encounter arrangements where certain restrictions must be adhered to. These restrictions may include restrictions on certain positions. They say that the word starts with W. So there's a condition there. There's a restriction there. All right. Or a requirement for certain objects to be grouped together. They say M and N must always be next to each other. So when that comes, this is the guideline that you have to use. When objects are grouped together, treat those objects as a single item that can be moved within an arrangement. So if you are having a weight, maybe a weight, right? And they are saying W and R must be grouped together. So you must make W and R one object. This one object can move between which weights? It can move between O and D, which means this WR can come here, can start, or can come here because it has to move together. Then you have D, all right? Or this WR can come here, you see? So that's what can happen there. So that is the movements, different movements. We have others. You can also have the D starting, all right? O, and then the WR, and all those other possibilities. But I'm just trying to show you that the WR moves as one unit. So if they are saying you are grouping the letters or whatever objects together, you move them as a single object, all right, that can be moved within an arrangement. If the position is fixed, they say the word must start with W. then we fix that object in that position such that it cannot be moved with respect to the other letters. Remember, you are doing arrangements, all right? If the objects are grouped and the position is specified, we fix the group in that position, but remember that within the group there can be further arrangements. You see, with our WR, it can also be RW. So we need to consider that as well, the interchange within the grouping. All right, fine. Now, let us look at arranging the rest. All right, sometimes it becomes very difficult to count what is expected. All right, it becomes very, very difficult to count what is expected. So as such, we introduce a rule that will allow us to be able to count that. Suppose that, for an example, I'll give you an example. You are given 5 letters, or let me make it 4, all right? 4 letters, all right, of the word read, all right? And then they say R and E must not be next to each other. R and E must not be next to each other. If you look at those possibilities, all right, it means there should be a space between R and E. All right, you look at all the possibilities that present at least one space between R and E. So you'll be looking at all those different possibilities that involve where you have a space between R and E. All right. So you can have R and E. So you are going to present all the possibilities where R and E are not next to each other. And all these possibilities, to count them, it becomes very, very difficult. So when that happens, we are going to use the NOT rule. We are going to say we count all possibilities, right? If it's 5 possibilities, the total possibilities, and we count where R and E are close together. When they are next to each other, if it's 2 possibilities where they are next to each other, out of 5, we know we are going to subtract 2 from 5. The remaining is 3. So we are going to count by difference, all right? We are going to use the remaining. So that is why we are saying we are counting the rest, all right? We are counting the rest. Let me present another example. Suppose that you have a code with 4 digits, all right? And digits are numbered from 1 to 7, and there's repetition. You are allowed to repeat. And then they say to you, 2 must be used at least once in the code. At least once. You see, if they say at least, it means you can use 1 or more 2s, right? If you use 1, you will have 2 here, all right? Or 2 here, moving in different positions. 2 here, or 2 there, if you use it once. But when they say at least, it's 1 or more, which means that you can use 2 of them in different positions. All right? In different positions. You can now also use 3 of them in different positions. So you see the options become many and it becomes difficult to count them, right? So we are going to use what? The NOT rule, where we will say now we are going to consider the possibilities where there is no 2 that is used. So if you have the total possibilities, subtract the possibilities without a 2. The remaining possibilities would be possibilities where at least 1 2 has been used. So that is why we sometimes have to go through the NOT rule, all right? All right, now let's look at a few examples, all right? So the examples will encompass everything that we've done from where I had led you to what? arrangements with what? With restrictions. Now let's check. 3 boys, Sipho, Mandla, Clive, and 2 girls, Bongiwe and Retumetsi, are to be seated next to each other in 5 different seats to take a group photo. Alright, so we have 3 girls. Oh no, it's 3 boys. We have 3 boys. Plus we have what? 2 girls. They want to take a group photo. So it's a total of 5 individuals. How many different ways can the 3 boys and the 2 girls sit in a row if they can sit in any order? So the order does not matter. So you have 5, which means that in the first chair we would have 5 options, second space 4 options, and so on. All right. And then the second one, how many ways can they sit in a row if Sipho and Bongiwe must sit together? See, now there's a grouping coming in here. How many ways can they sit in a row if Sipho and Bongiwe refuse to sit together? All right. So now we need to be strategic. Now let's check. All right. So now, without any restrictions, we are going to have 5 spaces. 3, 4, 5. 5 options for the first position. 4 options for the second position. 3 for the third, 2 for the fourth, 1 for the fifth. So we get that this would be 5 because it decreases until 1, 5 factorial, which is what we have there. We have 120 different ways, all right? Now, if Sipho and Bongiwe must sit together, what we need to do here is we take Sipho and Bongiwe. We make them one object because they need to sit together. We make them what? One object. And then from there, the remaining ones, 1, 2, 3, all right? So there are 3 that remain, all right? So there are 3 remain, all right? There are 3 that remain. So now we have 1 object, we have the 3 that remain. So when we treat this as a single object, how many objects are there to arrange? Therefore, 4 objects to arrange. Where does this 4 come from? It comes from the fact that we have Sipho and Bongiwe being a single object, and then we had 3 that remain, all right? So which makes 4. So we have 4 objects to arrange, and to arrange these 4 objects, we can do it in what? 4 factorial ways, all right? 4 factorial ways. But then we also have Sipho and Bongiwe that can interchange positions. We can start with Bongiwe and then Sipho, and then we can do that in 2 factorial ways, all right? So that is what we need to do here. 4 factorial times 2 factorial, where the 4 factorial represents what? All objects, all right? And the 2 factorial represent what? Sipho and Bongiwe can change positions. So they can do it in 2 factorial ways, all right? Now let's look at the third one. It says, how many ways can they sit in a row if Sipho and Bongiwe refuse to sit together? If they refuse to sit together, we are going to count by difference. So we're going to say total ways would be total possibilities without restrictions, all right, minus possibilities where Sipho and Bongiwe are next to each other. All right, so we will count by difference using the not rule. Because if we are to try to arrange them, if we have 5 spaces, 1, 2, 3, 4, 5, it means we have to leave 1 or more space between Sipho and Bongiwe, starting with Sipho first, and then have other options where we start with Bongiwe and leave 1 or more space. So it will create a lot of possibilities there, which becomes tedious to calculate or count, so we are going to count by difference. So possibilities without restrictions, that is 5 factorial that we got when we started, and then minus possibilities where Sipho and Bongiwe are next to each other, that we calculated in B 4 factorial times 2 factorial. That gives us 72 different ways. All right. Let's move on. Now, this is the activity. Calculate the probability that the boys and girls sit in alternate order. All right. So to do that, I'll give you just 3 minutes. All right, for the activity. 3 minutes. Please be quick. Your 3 minutes time starts now. Right, hello and welcome back. Let's look at the problem that I gave you. It's a continuation of what we were doing in the previous slides. We are given 3 boys, Sipho, Mandla, Clive, and 2 girls, that is Bongiwe and Reitumetse, to be seated next to each other in 5 different seats to take a group photo. Calculate the probability that the boys and girls are arranged in alternate order. So our alternate order, boy, girl, boy, girl, boy. All right, that is the alternate order. Now let's check when we start with a girl. It will be girl, boy, girl, boy. We are left with a boy. So this here is not the recommended alternate order. They do not alternate because at the end you have the 2 boys. So they alternate to a certain degree, but not the whole arrangement is alternating. But if you check with this one, boy, girl, boy, girl, boy. So there's only one way of having them to alternate. That is if you start with a boy. All right. So we're going to be looking into that one. So if you start with a boy, 1, 2, 3, 4, 5. So you have a boy here, a girl here, a boy there, a girl there, a boy there. So you ask yourself, what would be the number of ways in which they can alternate? How many boys do you have? 3. So you'll have 3 options for the first seat where the boy should occupy that seat, and then you will have 2 options for the second seat. Remember, I'm looking at boys only for now. I know they alternate, but I'm looking at boys only for now. So you started with 3 boys now, which means in the second boy seat you will have how many? 2 options. In the last boy seat you will have 1 option. And then for the girls, in the first girl seat, you would have 2 options because there are 2 girls. In the last girl seat, you'll have 1 option. So you can multiply these together to get the total, all right? But they say calculate the probability, which means you are interested in having an event, all right? And then a sample space, all right? Sample space is where there are no restrictions, all right? Fine, let's check that out. There's only one way this can be done, all right? It's boy, girl, boy, not the other way around. So how do we do that? I've already explained that, all right? And then from there, let's look at how we can calculate our probability. The number of elements in the expected set. Remember, the probability that boys and girls are arranged in an alternate order. So the event is what? Arranging boys and girls in an alternate order. That is the event, all right? And then what is the sample space? The sample space is number of possibilities where there is no restriction. We've calculated it in the first problem. We said total arrangement would be 5 factorial, which gave us what? 120. We did that in our previous slide. So the probability would be number of elements in the event divided by that in the sample space, which gives us 12 over 120, which is 1 over 10, all right? Which is 1 over 10. So that is how we've calculated our probability there, all right? Now I want us to move on. Another example, we are dealing with the word chemistry. How many ways can letters of the word chemistry be arranged if the word starts with C and ends with a Y, all right? So the word starts with C and ends with a Y. How many letters are there? 1, 2, 3, 4, 5, 6, 7, 8, 9. It's 3, 6, 9. So it's 9 letters. All right, so we have to open 9 spaces. 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. You are told you have to start with C and end with Y. So because they are telling you what to start with, you are going to fix C here and fix Y there. What does that mean? It means that you have to arrange the rest. Arrange the rest. Already C and Y have been placed for you, so you have to arrange the rest. So how many letters are you arranging? 7. So this would be 7, 6, 5, 4, 3, 2, 1. So it means that now you will have this as what? 7 factorial. So the answer would be 7 factorial. However, you can still ask yourself, how many options do I have of having a C in the first position? It's 1 option. Having a Y in the last position, it's also 1 option. So this can be adapted to what? 1 times 7 factorial times what? Times 1. All right. So let's check here. Start with a C and end with a Y. 1 times 7 factorial times 1, all right? So the 7 factorial is the rest of the letters, the remaining letters. This one is 1 option for what? Starting with C, 1 option for what? Ending with Y. All right? The word starts with a vowel, all right? So now you have another problem. You have to start with a vowel. All right. So 1, 2, 3, 4, 5, 6, 3, 6, 7, 8, 9. If you want to start with a vowel, so what are your vowels? Your vowels are available here: A, E, I, O, U. These are the possible vowels that we have in the English alphabet. But in the word that we only have E as well as I as our vowel. So how many options do we have of starting with a vowel? It's 2 options, because we can start with an E or start with an I. Someone can write this 2 times and start with an E as the first case, start with an I as the second case. But I'm saying we have 2 options of starting with a vowel. Then we have to arrange the rest. The rest are how many? 8. So we have to arrange the rest. Let's check here. So it's 2 options times what? 8, 7, 6, 5, 4, 3, 2, 1. All right. Because this starts with an 8 and goes down to a 1, we can use it as what? 8 factorial. All right. So this is the 2 options for what? For the vowels. All right. This is the 8 factorial for what? For the remaining letters. For the remaining letters. All right. Now let's look at the last one. M, I, and S must be grouped together in any order. M, I, and S must be grouped together in any order, all right? Now, when we want to group them together in any order, this is what will happen. M, I, and S, M, I, S. If they are to be grouped together in any order, we make them one object. All right. When we group, I did in the guidelines, I did tell you, we make it, whatever that we want to group, we make it a single object. One object. And then how many letters remain? We took out M, I, and S, we are left with 6. 1, 2, 3, 4, 5, 6. So, plus 6 remaining letters. So if we have 6 letters that remain, all right? If we have 6 letters that remain, and we have M, I, and S as a single object, it means that now there are 8 objects to arrange. Oh no, 7 objects to arrange. Where is this 7 coming from? It's the 1 plus what? 6 remaining letters, which gives us 7. So if we want to arrange these objects, we can do them, arrange them in what? 7 factorial ways, because it can be 7 times 6 times 5 times 4 and so on. So we can arrange them in 7 factorial ways. However, there is another option within these options. The letter M, I, and S can come back as MIS, right? MSI, right? SIM, SMI, right? And then IMS, all right? ISM. So you see, they can be further arrangements. How many of them? 1, 2, 3, 4, 5, 6. They can still be further arrangements within the M, I, and S. Yes, they are together, right? They are together, but they can be together in a different order. All right? They can be together in a different order. So they can be a further arrangement. Because there are 3 letters, it can be done in 3 factorial ways. And you know, 1, 2, 3, 4, 5, 6. I said 6. What is 3 factorial? 3 factorial is 3 times 2 times 1, which is 6. So there can be further arrangements there. All right? So that is what is happening there. Let me bring down the solution. So the 7 factorial is for all objects. All right. And then the 3 factorial is for what? MIS, interchange positions. they interchange position, so you get to that value there. All right, so you have to be smart about how you approach this. All right, now I have another activity for you. I will allow you to do this in 5 minutes. All right, for both the problems I give you 5 minutes. Please try to work as quickly as you can. It's still the same thing. Okay, let's just make it 4 minutes, 2 minutes per problem, because I see it's the same as the one that we did before. It's just that I've changed in the wording there. All right, so 4 minutes to do the activity, and your 4 minutes time starts now. Right, hello and welcome back. Let us work on these two problems. How many letters, ways letters of the word chemistry can be arranged if M, I, and S must be the first three letters, all right? So we need to start with what? MIS. All right. So although we are grouping them, but we are also now fixing them because they don't have to move with respect to the whole arrangement. So it means that the remaining six, 1, 2, 3, 4, 5, 6, the remaining 6 letters, M, I, and S, cannot move with respect to that. You can rearrange the remaining 6 because they said it must be the first 3 letters. So here, 6 remain. All right. So here, when you arrange, you are going to be arranging the 6 that remain, because remember, M, I, and S is not part of the arrangement because it is already arranged for us. They must be the first 3 letters in any order. All right. We are still going to take care of the any order. The any order means they can also interchange positions. MIS, you can have MIS, MSI, SIM, SMI, all right? You can have IMS, ISM. So you can rearrange them in any order as long as they remain the first 3 letters. So you can have further arrangement here, 3 factorial, which is for IS interchanging position. But remember, because they said must be the first 3 letters, it means you fix them in the first 3 positions. You can no longer make them part of the rest of the arrangement. All right. So if they said M, I, and S must be grouped together, it means the group can move with respect to the other letters. But now, because they said they must be the first 3 letters, they cannot move with respect to other letters. All right. Now, let's look at the last one. This is A, this is B. The last one says M, I, and S must be the first 3 letters. You see here in that order, which means the order cannot change. 1, 2, 3, 4, 5, 6. The order cannot change. They need to be the first 3 letters that way. MIS, that way, which means the only part remaining to arrange is the remaining letters, which can be done in 6 factorial ways. So we need to think deeply about how we do this, and it becomes a bit more easier if we think more deeply about it. All right, I'm moving on. Now, arrangement of identical objects. You saw with the word chemistry, intentionally here, I did not include any, I did not repeat any letter. All the letters were unique, all right? They were unique. Now, what if we have identical letters? Check on when we consider the word dead, all right? There are 3 arrangements, DAD, add, and double DA, that we can arrange this with, all right? If the repeated letters, the D's, are treated as identical, they are identical letters. However, if we treat the D's as unique letters, I will put subscript 1 and 2 for the different D's to show that we are treating them as different letters. You can see now the number of possibilities increase. 1, 2, 3, 4, 5, 6. So the number of possibilities are now more when we have what? When letters are treated as different. All right, so there are 3 different arrangements when letters are treated as what? As different. All right, now if we check here, because of that, we need to develop a way to be able to count if the letters are identical, because there would be repetitions that we will need to remove. All right, now let's check how we can do that. The above problem is only practical for short words. If we were given a word Mississippi, for an example, and it will be a tedious task to arrange these letters. So because of that, we'll formulate a rule that we can use to arrange longer words. All right, so we are saying the number of arrangements of n objects of which p are identical, q identical, r identical, and so on is given by n factorial divided by p factorial times q factorial times r factorial. So you always divide by the repeats. All right, so let's go back to the word dead. All right, the word dead. So how many letters are repeated here? Let me go back here. How many letters are repeated? You have 3 letters, D we have 2, and then A we have 1. So we have 3 letters. So to arrange these letters, we would say it's 3 factorial if the repeated letters are treated as identical. Then we need to not count them twice. To prevent that, we will divide by the repeated letters, which is 2 factorial. 3 factorial divided by 2 factorial is 3 times 2 times 1 divided by 2 times 1. This gives us what? 3 ways, all right? So there are 3 ways. We can see here 1, 2, 3, all right? So it's easier if we have fewer letters. But if you start having words like Mississippi, then it becomes a bit difficult to do that. So we have to use the rule, all right? Now let's look at an example here. Consider the word needed. How many letter arrangements can we make if we consider the 2 E's and the 2 D's as different letters? Now, good people, I need you to note something here. The question will always indicate that letters should be different, all right? But if they are identical, the examiner is at liberty not to indicate. So you will treat them as you see them. So if you look at the word needed, you can see those E's are the same. So you will treat them as the same. Unless if they said to you they are different, then you will put 1, 2, and 3 to make them unique. All right? Now, if we consider the 2 E's and the 2 D's as different letters, let's check now. If we consider them as different letters, then the arrangement would be 6 factorial because we have 1, 2, 3, 4, 5, 6 different weights. All right? So if they are different, it's needed. All right? So it's E1, E2, E3, D1, and D2. So it's different letters, so it's 6 factorial. 6 times 5 times 4 times 3 times 2 times 1. All right? But if we consider the 3 E's and the 2 D's as identical letters, then we will need to count N, we have 1. E, we have 3. And then D, we have 2. In total, we have 6 letters. So to arrange this, we are going to say total arrangement would be the total, which is 6 factorial, divide by the repeated letters, E's that are repeated, it's 3 factorial. This 3 factorial is for the E's, times 2 factorial, and this 2 factorial is for the repeated D's. So you get your answer from that, all right? So the second one would be 6 factorial divided by 3 factorial times 2 factorial. Now, the arrangement must start and end with the same letter. Now, we have a trick here. If you start and end with the same letter, you can start and end with an E, all right? These are repeated letters. 1, 2, 3, 4, 5, 6. Or you can start and end with a D. 1, 2, 3, 4. You see, so because you have those two options, you know or in probability is the union, so you would have to unify the two by adding, all right? So we would have that we can start and end with an E. If we start and end with an E, that is case 1, all right? These are the arrangements. How do you work them out? If you started and ended with an E, how are you going to do this? You start and end with E. So how many letters will remain? You have N, which is 1. You have E, which is 1, because you started and ended with it. You have D, which is 2. So you have 4 letters remaining. That's where the 4 factorial comes from. But the D's are repeated. So you're going to divide by 2 factorial, which is for the repeated D's. That is case 1. Now we can present another case where we start and end with a D. If we start and end with a D, we have a D here and a D there. So we have 4 remain, all right? So in those 4 that remain, we have N, which is 1. We have E, which is 3, all right? And then this gives us 4 letters, so we can arrange them in 4 factorial divided by 3 factorial, where this 3 factorial is for the repeated E's. That is when you start with what? When you start and end with D. So we have the 2 cases. We can just add the possibilities for the 2 cases. We get that this is 16 different arrangements. All right. I hope that you are actually getting this. All right. This is an example, an activity which we were supposed to give you. I'll go through this activity with you, right? I'll go through it with you quickly. We have the word effervescence. Repeated letters are treated as different. So now, if we check here the E's, how many E's do we have here? 1, 2, 3, 4, 5. 5 E's. It's 1, 2, 3, 4, 5. And then F, it's 1, 2, it's 2. And then R1, all right, V1, S1, C2, C it's 1, 2, and then we are left with N, which is 1. So we have a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 5, 7, 8, 9, 10, 11, 12, 13. We have 13 letters. So in order to arrange them, let's check. You see here, they said how many unique ways can the letters be arranged. You were not told whether there is a letter that is repeated or a letter that is not repeated. So you will just go straight to that, and you have that the total arrangement would be 13 factorial divided by 5, which is for the repeated E's, 2 factorial, which is for the repeated F's, and 2 factorial, which is for the repeated what you call the C's. All right. Now the second one, how the 4 letters are arranged if R, V, N, S, and N in that order are the first 4 letters. So it means that you have R, V, S, and N as the first 4. You fix them there. So you look at the remaining letters. It's 9 of them. In the 9 remaining letters, you still have the E's, which are 5 repeated. You still have the F's, which are repeated. You still have the C's, which are repeated. All right. And then the last one, the 4 letters R, V, S, and N in any order. All right. So if they are in any order, they are part of the arrangement in any order. All right. So how many letters do you have there? You have are the first 4 letters. So you fix them in the first position because they are the first 4 letters. How many letters do you have remaining? It's 9, and then 5 factorial, 2 factorial, 2 factorial. But because they are in any order, it means that they can also interchange position, these 4 letters, 1, 2, 3, 4. So they can do that in 4 factorial. That is why we brought in the 4 factorial there. All right. Let's quickly work with digits as we conclude. There is a difference between digit numbers, a digit code and a digit number. A code can start with a 0, but a number cannot start with a 0. For an example, 012 is a 2-digit number because a number cannot start with a 0. So we only start counting when it becomes significant. All right. A code can start with a 0. For an example, 012 is a 3-digit code. All right. Now let's look at the last example before we close. The digits 1, 2, 3, 4, 5, 6, 7, and 8 are used to make a digit number. How many unique numbers can be formed? How many 2-digit numbers can be formed if repetition is allowed? Let's check. If repetition is allowed, we have 2 digits, right? And then we have 8 available digits. So we have 8 options for the first position. And repetition is allowed, which means we have 8 options for the second position as well. All right, so that gives us 64. The second one, how many 4-digit numbers can be formed if repetition is not allowed? Now you have 4 spaces, all right, and we have no repetition. So the options that we have for the first position is 8 for the second, because there's no 0 there. Remember, it's a digit number, which means we cannot start with a 0. But fortunately, in our sample size, there is no 0. So it's 8 options for the first position, 7 options because repetition is not allowed for the second position, 6 options for the third position, 5 options for the fourth position. So that's how we can actually work it out. The total numbers is 64 numbers. Now, how many digit numbers can be formed between 4,000 and 5,000? And repetition is allowed. So we want to form a number between 4,000 and 5,000. Let me just check here. Between 4,000 and 5,000, which means we have to start with what? We have to start with a 4. Remember, if you start with a 5, you are going to have numbers that are bigger than 5,000 because there is no 0 there. And repetition is allowed, all right? So they are between 4,000 and 5,000, which means for the first position, the range here out of the available numbers, repetition is allowed. So the range here would mean that you can start with 4, and then the lowest number, the code can start with 4111 and can end with 4, and then from there the highest number would be 888. That is the range of codes that you can have, all right? Because once you start with 5, then you cannot have any other numbers because 0 is not part of the sample. So the code must start with 4. So the first digit must be a 4. And there's one option of starting with 4 because there's only one 4 there. And then the rest of the digit, they are allowed to repeat. So you can have 8 here, 8 there, and 8 there. All right? So that's what you can have there for that particular code. So you have 1 times 8 times 8 times 8, which is 512 numbers, all right? So now, obviously from there, it means that we've completed what we wanted to do, right? This was the activity I would have given you, all right? This was an activity I would have given you, but because of time, we are not going to be able to do the activity. Right now, let's look at the summary. The counting principle is concerned with the number of options or possibilities available of doing a specific task. That's what we spoke about. And we said we are going to use the factorial notation to congest these big products, and it's going to be a very useful tool in the counting principle. And if objects are grouped together in counting principle, they should be treated as a single object which can be moved within an arrangement. If the position of the object is known, we need to fix that object in that specific position. All right. When dealing with codes, remember that a digit number cannot start with a 0, but a digit code can start with a 0. All right. When dealing with arrangements of letters and books, please check whether they are identical or different. Because if they are identical, then you need to make sure you don't count twice by dividing by those that are identical. All right. Now let's preview our next lesson. Our next lesson is next week on the 27th of August 2025. We start at 2:30 to 4, and what we'll be doing is we will be revising paper 1 and paper 2. On paper 1, we will be looking at our number patterns, and on paper 2, we'll be looking at Euclidean geometry as part and parcel of revision in preparation for the preparatory exam. So this would serve as part 1 of our revision. All right, good people, thank you very much for tuning in. Please make sure that you take care of yourselves and you take care of each other and you practice mathematics. Goodbye.